Hello, I'm Derek Hitchens, and I'd like to talk to you today about systems engineering. Systems engineering was forged in the white-hot crucible of the Cold War on particularly vexing problems of the time: atomic energy, defence and aerospace. And it addressed difficult problems: how to meet a Soviet air standoff weapon threat, how to put a man on the moon. So SE systems engineering became seen as a major problem solver. And the systems engineering methodology, or systems methodology, was a way of doing things. Systems engineering then was a heavyweight, major, large-scale problem solver of the time, where a problem was of the sort how to achieve a really challenging goal. And systems engineering addressed the problem, conceived potential answers, and provided a complete, viable solution. At the time, systems engineering was king. So what is a viable solution? Viability is the ability of a thing, an organism, a system, an idea, to maintain itself or recover its potentialities. Whence, viable system, where a system is a complex, organised whole or body of material or immaterial things. A viable systems model is a scientific model of the organisation of a viable or autonomous system, and we'll be seeing one of those later. So, what makes a system viable? Well, the ability to survive and maintain itself, to overcome problems, threats and resource shortages, and the ability to recover its potentialities. Viable systems are autonomous and have both ways and means to recover without external help, which suggests that they have a significant degree of complexity. A viable system is one that can survive, to function, perform and even thrive in its natural but inevitably changing environment. Systems engineering emphasis is on the total system environment interaction, whence the acronym SMESH: S for survive, external threats; M for maintain, internal threats; evolve, that's adapt, renew or improve; synergize, cooperate, coordinate and control; and homeostasis, maintain the dynamic equilibrium and the internal environment within the system. These are all aspects of viability, and they have significant impact on any hardware that's involved. Each viable solution will have all it needs to organise, manage, function, operate, control, and so forth. And much of this seems to be about people, their capabilities, communications and welfare, rather than just being about technology, structure and form. Some examples: Apollo, Linesman, Far Side of the Moon, Mars colony. Imagine what a viable Mars colony disconnected from Earth would need, not only to survive, but to flourish, explore, build, expand, adapt and evolve, and reproduce, which would itself require a viable gene pool. And that whole would be a systems engineering end product, a viable autonomous system solution. Let's have a look at Linesman. It was started in the 1950s and 60s, and Linesman was an advanced, highly complex air defence system for the whole of the UK. It was viewed as a single system within the so-called total weapon system concept. Now, this may look complicated to begin with, but the wavy line shows the interface between the two setups. They got the Soviets to the right, coming into the eastern seaboard of the United Kingdom with their Soviet standoff weapons and their standoff jammers. And on the left we have a number of large radar sites marked with the gold stars at Neatishead, Staxamall, Bulmer and Bishop's Court. These are up and down the coastline of the United Kingdom. Pictures of the air threat were collected from these radars and all sent to a building shown on the left of the L1 Operations Control Centre, from whence aircraft from various Lightning interceptor bases were scrambled and directed via data links automatically onto the standoff weapon threats. Very complicated, very large, and covered the whole of the nation. It was, however, ahead of its time, built, tested, but never fully implemented. Besides, the threat never materialized. And then there was Apollo, which consisted of very many parts to make it a complete viable system. And the viable system I'm referring to here is the whole of the NASA exercise. So total system architecting and implementation planning, program management, research and development, engineering, operator training, telemetry, communications, operations planning and control. It was a vast operation. We tend to think of Apollo as being only the actual missions, but that was, in some ways, a small part of the whole, although probably the most important part. Here's an exercise, far side of the moon, a Lunar Deep Space Center, the LDSC. Let's see. We're approaching our base, entering the base, and it's a dual-purpose base. For astronomy, there's a long base interferometer, part of which is on the moon, and for acclimatizing astronauts returning from deep space missions. It's underneath the regolith to protect against impact and cosmic particle damage, and it's on the far side of the moon to minimize interference from the Earth. When you analyze it, you find that there are basically 4 functional systems there. There's a base command system, a logistics system, an operations system, and a resource management system. And you can see how they're all connected to each other and to outside agencies. Looking inside each of those, you can see that there is a significant amount of organization and activity. The most interesting one, perhaps, is the operations subsystem shown on the right, with things to do with astronomy and things to do with reconditioning astronauts and rehabilitating them. And then there's the Mars colony. This is a conceptual initial colony. There appears, by looking at the picture at least, to be no integration with the land yet. They are temporarily trapped in their structures. But they will be mining for minerals and water ice. And this lot may be viable in the short term, but clearly needs a lot more if it's going to flourish. In fact, the long-term viability has to be in serious doubt for such a colony. Perhaps we should consider terraforming instead. So now we've seen some typical viable autonomous systems, and we can see that they consist of a number of parts. There's the mission system, which does the business. There's an operator and user support, which looks at training and retraining operators and users, and helping them develop planning and tactics. And then there's engineering support, looking after all the technology. And then there's a fourth party, which is marked here at the bottom, which is marked post-design services, which is about things like performance monitoring, modifications, continual redesign, continual upgrade. And that maintains the whole is a viable system. All 4 parts make up the viable system, although the mission system itself may be viable while it's on a mission. Looked at from a customer's point of view, viable systems are to be expected. You can see on the left a creative organization, and it's not only creating the operational system, but it's also looking after modifications and upgrades, maintenance, servicing, and probably the operator training system too. And as it says, would you buy a car, a dishwasher, or a combat fighter that could not be operated and maintained? Unlikely. So here we have a basis for a viable systems model that I promised you earlier. We have the viable body, we have some intellect, a brain, we have operations functions, and the last is a few of just the function management. And you can see at the top there is an operational environment, at the bottom a resource environment. And the mission management takes information from the operational environment, establishes its objectives, formulates strategies and plans, executes the plans, and cooperates with others in the environment. At the bottom, resources. All one can do with resources is acquire them, store them, distribute them, and convert them for use, disposing of any waste in the process. And in the centre we have SMESH again, survival, maintenance, evolution, synergy, and homeostasis, providing a solid basis for all the others. Notice that mission and resource management manage the flow and flux of information, energy, and substance through the open system. Systems methodology, the basic concept. We start with a real-world problem, which we take into a system domain to do work, systems work, and then we come out from that with a real-world solution. This is not engineering, although engineering may occur in the real-world part at the bottom. Systems methodology and the systems activities take place in what we might call the system domain shown at the top, and they are continually interacting, of course. A typical systems methodology might follow some sort of procedure: understand the problem, develop purposeful solution concepts, accumulate necessary functions, synthesize a system design, map functional design onto physical, specify the whole, and synthesize fit, form and function, and so solve, resolve and dissolve the problem. You can put this into an ontological map, which may make it simpler or not, depending on your point of view. Now, before you balk at that and look at the numbers, you follow the numbers 1, 2, 3, 4, 5, 6 and 7, which correspond to the numbers on the previous slide. I won't go through that. It's something you should read in your own time if you're interested. So, moving on, where is systems engineering now? By 1980s, it had become the touchstone of creativity, innovation and complexity management. But the Cold War ended in the late 80s, and reduction in major defence and aerospace contracts left systems engineering teams and houses dispersed, along with their important corporate systems methodologies and expertise, which had been worked up over decades. By 1990, the US recognised a shortage of systems engineer, and INCOSE was formed to recruit them. But INCOSE principally attracted engineers, not systems methodologists, operations researchers, system scientists, physicists, biologists, management scientists, psychologists, anthropologists, and so on. And the power of systems engineering is partly in the methodology and in the team, with its different yet complementary disciplines and its system tools and methods, which all form part of the methodology. INCOSE set about reinventing systems engineering, an engineer's alternative vision, in fact, in what turned out to be the engineering of systems. But so far, there has been no systems methodology recreated. So where is it now? Well, engineering of systems is well established within INCOSE. It offers a practice for sound engineering. Systems engineering of the Cold War variety is no longer needed, some say, because today's customers know exactly what they want, don't they? And there are no more problems of the how to achieve a really challenging goal variety. Or are there? Population growth, global warming, extreme weather systems, non-fossil power and energy systems, increasing population density, integrated transport systems, globalization, national IT systems, national health systems, asymmetric conflict and Islamic terrorism, and the rise of the robots, continued exploration of the solar system. Note how many of the above issues are interrelated, as shown on this causal loop model. Notice from the figure how extreme weather threatens globalization in the midterm, hence threatens our international imports of food and raw materials. And green energy may actually encourage population growth, apparently. Systems engineering may be able to tackle the parts and the whole of this set of problems, however, if solutions exist, that is. And it's not obvious that solutions exist to the population growth problem. There are autonomous, intelligent artifact systems, robots, automatons. Designers are creating more capable robots. And the time is right for such autonomous systems to start becoming more intelligent, to make decisions and choose between options, which involves ethics, morality, beliefs, conscience, and tacit knowledge, which is tricky. Medical work, nursing, exploring Mars, and the infamous Lockheed Martin F-35 Lightning Mark II, which is due in 2015, 16, 17. It's taking a long time. What is this? This is a typical assemblage of tools and their points of application within the progress of the systems methodology, which is shown by the arrows, the big arrows. The tools are context independent, but have in common their facility for reducing information and configuration entropy, leading from a disordered, perhaps even chaotic issue, to an ordered, specific solution system design. So systems engineering, it's in need of updating. It works for large and nowadays not so large problems. Essential ingredients? Well, it needs a ready supply of problems. It needs a maturing systems methodology for today's and tomorrow's problems and solutions. Reasonably bright systems architects, hard and soft scientists, operation researchers, analysts, and domain experts. It needs system tools, methods and techniques. These are the engines of the systems methodology. And it needs practice, lots of practice, which integrates the team and matures the methodology. You need practice. How do you get to Carnegie Hall, lady? You've got to practice. And here we see, as the final presentation, an overview of systems engineering, with the systems methodology bridging from the problem space at the left to the solution space at the right. Thank you for listening.